Okay, let's start our lecture today. So today we will discuss about waves. Yeah. I think there are two kinds of waves we will discuss. First is the general properties of waves, and then the second is waves about sound. Yeah. Or we specifically discuss about mechanical waves. Okay. Okay, in this section, we will discuss about transverse waves. So the objective of our study in this section, there are 3 points or more than 3 points here. I think we need to identify the three main types of waves, distinguish between the transverse and longitudinal waves, and given a displacement function for a transverse wave, determine the amplitude Ym, yeah, angular wave number k, angular frequency omega, and phase constants pi, yeah, and the direction of travel to calculate the phase kx plus or minus t plus phase constant and the displacement at any given time and position. Yeah. Okay, and then displacement function sketch the graphs of transverse waves and given the graphs of displacement versus time for a transverse wave and determine amplitude Ym and period t. Yeah. And then phase constants, apply the relation between wave speed, distance, and then the relationship between speed, v, angular frequency omega, angular wave number k, and wavelength lambda, period t, and frequency f. Okay. Okay, the first is types of waves. Actually, we need to define, yeah, describes three kinds of waves. The first is mechanical waves. So mechanical waves, it means that governed by Newton's law, and they can exist only with a material medium, such as water, air, and rock. For example, is water waves, sound waves, and seismic waves. We know that water waves, uh, if we go to the beach and then or lake, we will see the water waves, and then sound waves and seismic waves. And the second types of waves is electromagnetic waves. So the electromagnetic waves require no material medium. Yeah. Light, like light, yeah. Light waves from stars, for example, travel through the vacuum of space. Yeah. For example, for sun and from sun to earth, yeah, this is the type of electromagnetic waves. So we know that this one in the vacuum of space, right? And then the characteristic of electromagnetic waves, it travel by the same speed, is defined by c. Yeah, c is around 299 or 3 times 10 power 8 meter per second. This one is the speed of light, okay, or the speed of electromagnetic waves. And then the third types is matter waves. These waves are associated with small particles like electrons, protons, and other fundamental particles, and even atoms and molecules. Yeah, because we commonly think that these particles are as constituting matter. Yeah, so we know that this one is matter waves. Okay, mechanical waves, electromagnetic waves, and matter waves. Okay, this one is the types of waves. Okay, and then this one is the example of transverse wave. Okay. The sinusoidal waves is sent along a string. Yeah. If we make the string here is on vibration. Yeah. And then the energy will be transferred. Yeah. So we know this one is the kind of transverse wave. Yeah. For example, this one the displacement is to up and downs. Yeah. And then the wave's speed will be to the right side. Okay. This one is the sinusoidal wave. Okay. And then the second type, yeah, this is the longitudinal waves. Yeah, the first is transverse wave and then longitudinal waves. For example, like sound. Yeah, sound wave is set up in an air, yeah, filled pipe by moving a piston back and forth. Yeah, so in this case, the displacement will be parallel, yeah, to the direction in which the wave travels. So this one is type of longitudinal waves. Yeah. But from transverse wave, this one is not parallel, right? Okay, but this one is parallel. Yeah, the direction of the waves and the displacement of the waves. This one is parallel. So this kind of wave is called longitudinal waves. Okay, for example, like sound and then spring waves. Yeah, these are kind of longitudinal waves. Yeah, commonly waves we can set as a sinusoidal function. Yeah. So this one is the 5 snapshots of y versus x is at a constant time of a string waves traveling in a positive direction along x-axis. And then we know that this one is ym. Yeah, ym is the amplitude of the wave, and the displacement for one wave we call lambda. Lambda is the wavelength. Yeah. Lambda is the wavelength, and then yeah, x is the position. Okay, so basically in general we can write the equation of wave is like this one. Yeah, y the function of x and time. Yeah, ym sinusoidal of kx minus omega t. Okay. Remember in the before we studied what periodic function, right? The oscillatory function. To the here there is one term of kx. So k is related to lambda here. Lambda is the wavelength. Okay. Now here that right larger y function of x would find. No, this one is y cap minus ax minus omega t. Yf equal the amplitude of the wave. Okay. And then this one sinus kx minus omega t. This one is the oscillatory term, oscillating term. And since this one is a decimal function, yeah. Then we know this one. So it's all from sinus to at the end. One is oscillating term. And then this one is like angle, right? In sinus to the function like angle. But in this case, this one is phase. Okay. And then K is wavelength. Okay. K is default angular wavelength. One is wave number. And then omega is angular frequency. X is the position and T is pi. So X is the position of wave and X is. So this one X is the position 1 in meters and T is pi in second. So angular frequency in radian per second. And this one is 1 per meter. Okay. And then the relation of wave number with lambda. Lambda is the length of one wave. So as wave x and y, since this one Okay. One wavelength is for this one is one. Another is wavelength. Then the relation of when with K is unknown number. K is pi decimal. And omega, this one is the frequency. Frequency is pi by T. So capital T is the period. The period is time to make one reach. Lambda is the position of the side bridge. But T is time to perform of lambda. Very second. And the relation of T, period and frequency is 2 pi times 6 1 frequency is 1 period. T. Okay, this one is very important parameters of waves. So we know K wave numbers or angular wave number, and then angular frequency and frequency. Okay, any questions about properties of waves or wave parameters? Yeah. Okay, and then what is the wave speed? Wave speed is the distance divided to time, right? So if we have like this one is 2 snapshots of the wave at time t equal to 0, and then after t equal to delta t. So there is the displacement v. Okay, so displacement divided to time equals speed, right? Or equal velocity. Delta x divided to delta t. Okay. So we can calculate the speed of wave, yeah, using this one. Okay, this one is delta x divided to delta t. Yeah. V is equal to omega divided to k. Yeah. Omega divided to k is equal to lambda divided to period. Yeah. Omega is what? P is omega divided to t, or lambda times divided to t. This one is this one lambda and then times one is we know lambda is 2 pi divided to k, and then t is this one 2 pi divided to. So if we substitute to this one, pi divided to k, and then 2 pi to t, so one is omega. So omega divided to k. Omega divided to k is wave speed. So if we have the equation of waves, we can determine the velocity, can determine the speed. Yeah. So by this one, for example, y x point t, yeah, ym sin kx plus omega t. So we can calculate the speed by dividing the omega and then k. Yeah. Omega divided k. So this one is the speed of the wave. Yeah. Okay. Any questions? Okay, yeah, basically this one for transverse wave. And then for string, yeah, wave speed on a stat string. Yeah, for example, if we play string like guitar, okay, or violin maybe, or another music tools. Yeah. Okay, and these learning objectives are calculate the linear density mu of a uniform string in terms of a total mass and total length. Yeah. Find the relationship between wave speed, tension, tau, and linear density mu. Okay. Okay, this one is the linear density relationship to wave speed of for stretch string. Yeah. So we can define this one. Mu is the mass of string divided to the length of string. Yeah. So this one is called linear density. And then the speed of waves here is square root of tau divided to mu. Yeah. Tau is tension. Yeah. The tension in the string. Yeah. Okay. We have string. Can calculate this the speed mu. Tau is the mu. Tau is the tension of the string. The mu here is the mass of the string divided by the length of mass divided. Okay, here is the linear density. Shooting of a mass with one. And then energy and power of a wave traveling along a string. We will calculate the average rate at which energy is transported by transfer waves. Okay, we remember that kinetic energy, right? Kinetic energy is mass v square divided to 2. Half mass is v square. We know here decay is the kinetic energy, and then dm is the mass. Yeah. So the rate of energy transmission, the kinetic energy decay associated with the string element of mass dm, yeah, half dm u square. Yeah. U is the velocity, right? So when we set up a wave on a state string, we provide energy for the motion of the string as the waves moves away from us. It transports that energy as both kinetic energy and elastic potential energy. Okay. So U is the transfer speed of the oscillating string element. Okay. Okay. This one is the rate of traveling wave, right? Okay. Decay half dm u square. And then the average power of or average rate at which energy is transmitted by sinusoidal wave on a stretch string is given by this equation. This one is the uh, P average. P is power. Yeah. Okay, yeah. Then next is the wave equation. Yeah. So for the equation given a string element, displacement as function of position, and then time, we can construct the wave equation. Okay. Okay. Before we need to use Newton's law. Yeah. This one like string, and then we can project the force. This one. F1 and F2, and then dx. This one is string element as a sinusoidal transverse wave. Yeah. So we will get the equation. The equation of wave is d del square y do x squared. Yeah. So this one is the general wave equation. Yeah. This one is the general waves equation. Okay. Then the interference of waves. Yeah. This one is the principle of superposition. If we have wave one and wave two, and then they will combine, so become resultant waves. Okay. Okay. Later we can calculate, or we can derive the equation. Yeah. But now I think we need to make sure first about the equation of waves. Okay. Okay. So we have the general equation. This one is y x point t, yeah, comma t. This one is ym, and then sinusoidal of kx minus omega t plus pi. Yeah. This one is the waves equation. Yeah. So by the speed of the traveling waves can calculate by, here. This one is the phase. So kx minus omega t, this one is constant. Yeah. And then we can take the derivation for this one. So ddt, yeah, from kx minus omega t. So this one is constant, and then the derivative of constant is 0, right? So we know that this one is k dx dt minus omega equal to 0. And so we'll get dx dt is omega per k. Okay, dx dt is velocity. Yeah. So we know the speed of velocity of waves is omega divided to k. Okay, so this one is the speed of waves. Okay, this one is the speed of waves. Then before we know the relation, yeah, that k is 2 pi divided to lambda. Yeah. Since k is 2 pi divided to lambda, and then omega is 2 pi divided to t, or 2 pi frequency. Yeah. So phi is equal to omega is 2 pi divided to t, and then k is lambda divided to 2 pi. Yeah. So this one is lambda divided to t. Okay. Or we know lambda times frequency. Yeah. So we know the speed of wave, we can use v is equal to lambda divided to period, lambda divided to t. Yeah. Or v is lambda times frequency. Yeah. So we can just use this equation. Okay, this one is also the speed of waves. Okay. Okay, and then we can see from this equation. Yeah. So for the direction of waves, we know this one is kx plus or minus omega t. Yeah. So if positive here, it means that to the left side. But if the sign is negative, it means to the right side. Yeah. So for example, this one is minus, right? So the direction of waves is to the right side. But if we have the sign here is positive, it means to the left side. Yeah. Okay, for example, for positive one, kx plus omega t, and kx plus omega t, this one is also a constant. So we can take the derivative of this one. Yeah. Okay, for example, the origin of equation is ym cos kx plus omega t. Yeah. Okay, this one ddt can take the derivative of kx plus omega t. Since this one is constant, so the derivative is 0, right? And then ddt k dx dt plus omega is equal to 0. So we get that k dx dt is minus omega. That's why since the sign is minus, it means that the speed is to the left side. Minus omega divided to k. It means the speed or the waves traveling to the left side. Okay. Yeah, but this one is to the right side. Okay. Okay. You know, I mean the direction of wave. Yeah. So if we know this one positive one, yeah, so it means the wave travel to the left side. If the sign is positive, yeah. But if the sign is negative, means to right side. Yeah. Okay, for example, yeah. For example, if we have wave equation x and t 0.00327 sin 72.1 minus 7 or 2.72. Yeah. Well, this one is x and then t. Okay. I mean it's 1 times x minus t. Yeah. Okay, so this one is k, right? K and omega. So we can take the speed of the waves. Yeah. So v is omega divided to k. Omega is 2.72 divided to it's around 0.03 meter per second. Okay. Since the sign here is negative, it means that to the right side. So the displacement is to the right side. Okay. Any questions? No. Okay. Then next is the transverse velocity and transverse acceleration. So we can calculate the velocity or transfer acceleration, right? So the transverse velocity is different to speed or the velocity of waves. It means that velocity of vibration, yeah, it is different to velocity of waves, yeah, or velocity of wave propagation. It is different. Yeah. So what is the transverse velocity? Yeah. Okay, so the transverse velocity, we can take the derivative, yeah, y x at position and time. Yeah. So this one is ym sin kx minus or plus omega t. Yeah. For simplicity, we take the positive one. It means to the right side. Yeah. So we can calculate the velocity of waves or transverse velocity here, u. Yeah. U is the derivative of dou y dou t. Yeah. Dou y dou t. Have you get this sign? Yeah. It at derivative, right? So it means that partial derivative. Yeah. Why we use this one? Since in this function we have three variables or two variables, yeah, x and t. But in this case, we only take the derivative for time, not for x. Yeah. So this one is a sign of partial derivative. Have you get it at calculus or basic mathematics, right? Yeah. Yeah. Basically, in derivative we use the dy dt, yeah, like this. But for this one, yeah, since the function is the function of x and time, yeah, this one is partial derivative, sign of partial derivative. It means that we take the derivative to the time, yeah, to respect to time, yeah. So we can take the derivative here. It means that dou dou t ym sin kx minus omega t. Yeah. So we get u. Yeah. This one is ym. So the derivative of sin become cos. Yeah. Cos kx minus omega t, and then times minus omega. Okay. So this one we can move to the beginning. Yeah. Minus omega ym cos kx minus omega t. U is the transverse velocity. Yeah. This one is the transverse velocity. Okay. Yeah. Any questions about this equation? Okay, we call this one as transverse velocity. Yeah. Okay, and then we can calculate the acceleration of transverse wave. Yeah. So we get the transverse acceleration. Transverse acceleration. So to get the acceleration, we can derive the velocity, right? Velocity u, and since we defined the velocity before as u du dt or do u dot t, yeah. It means that do with respect to time from u. U is minus omega here, minus omega ym cos kx minus omega t. Okay. So the derivative of cosinus, yeah, it becomes sinus minus sinus, right? So minus and minus become positive. So this one becomes omega square ym sin kx minus omega t. Okay. But actually, I think uh, before use sinus. Okay, minus omega t, and then this one since minus, then minus again positive, but there is minus. So this one is minus, right? Okay. Minus omega square ym sin kx minus omega t. So it means that this one is y. Okay. So we can write the acceleration as minus omega square times y. Y is the position or the displacement. Okay? So y is here, right? The original equation. Okay. Okay, so this one is the transverse acceleration. You can use this one or this one. Yeah, this one is the transverse acceleration. Okay. Okay. Yeah. Okay. Yeah. And then we continue to wave speed on a straight string. Yeah. So before we have discussed about this one. Yeah. Uh, like this, right? Wave speed of for a straight string. Yeah. How we get this equation? This one is the wave speed on a straight string. Okay, imagine if we have string. So in this case, we know this one as there is a tension. So the angle theta, and then this one is r. R is the radius. So there is the acceleration, right? The acceleration to the center of circle. Okay. Yeah, for example, this one is potentials tau, potentials tau, and then the length is delta L. Okay. Length is delta L. Okay. Okay, so the force here, we can calculate the force as 2 tau sin theta. Since the theta is relatively small, so we can use sin theta is equal to theta. Okay? Cool. So this one is 2 theta tau. So what is theta? Theta here is delta L divided to R. Okay. So this one is 2 delta L divided to R. Okay. I mean this one is tau. And then delta M is the mass of string. This one is U delta L. So A is the acceleration. A is the acceleration of string. We know that centripetal acceleration is V square divided to R. Yeah. So this one is the centripetal acceleration. Okay, by using the Newton second law, F is delta M times A. This one is the Newton's second law. So F here is the force, is equal to tau delta L divided to R. Okay. Tau delta L divided to R is equal to mass. Mass is mu delta L times A. Yeah. A is centripetal acceleration, right? V square divided to R. Yeah. Yeah. So this one is force. Yeah. This one is force. This one is the mass delta M, and then here is A, the acceleration, right? And then you can cancel delta L, you can cancel this one. Then R. So the equation becomes V square is equal to tau divided to mu. Okay, tau divided to mu, right? So we get that P is equal to the tension divided to mu. Yeah, this one is the speed for straight string. Yeah. Okay. Any questions for this one? Okay, and then next is energy and power of a wave traveling along a string. Yeah. Okay, so next is energy and power. Of a wave traveling along a string. Okay, before we have the energy and power. This one, right? The K is half dm u squared. And then the average power. Okay. Okay. So we know that U is to Y to T. This one is the speed. Okay. Minus omega Ym cos Kx minus omega T. Okay. And then mu is delta M divided to delta X. Or we can use that mu is dm dx. Or dm is mu dx. Okay. Okay. And then we can compute this one. The K is half the mu square. Yeah. So the k is half mu, oh, I mean this one, the mu square. Okay. So this one is half, dm is this one, mu dx, and then u is this one. Okay. This one is u square. Okay. Yeah, I think u square is relatively long. Then we can write this one. Okay. So the k half mu dx, u square is this one, right? Minus omega square minus omega ym cos kx minus omega t square. Okay. Okay. So we will get that half mu dx. This one is omega square ym square, and then cos square kx minus omega t. Okay. Okay. If we divide to dt, or we take the derivative of the dx dk dt, dk dt, this one become half mu dx dt. Yeah. Omega square ym square cos square kx minus omega. Okay, this one is phi, right? Dx dt is phi, or the speed of waves. Yeah. Half mu phi omega square ym square cos kx minus omega t. Okay. Okay, so the average rate, yeah, the kdt average is equal to the average of cos square. Yeah. The average of cos square is half. Yeah. So this one is half mu phi omega square uh, ym square times half. Okay. So becomes 1 divided by 4. Okay. Mu phi omega square ym square. Okay. This one is the k dt average. And then if you want to calculate the average power, yeah. So the average power is P average. This one is 2 times the k dt average. Okay. So it becomes half mu p omega square ym square. Okay. Okay. So we can calculate the average power. Okay. Yeah. This one is the equation of average power. Okay. So we can prove this equation. Okay. So equation average power. Okay. Half mu p omega square ym. Okay. This one here. Okay, so the general wave equation. This one is the wave equation. Can use the dou square y divided to dou x square is equal to 1 divided to v square dou square y dou t square. Okay. So this one is the wave equation. Okay, for example, for electromagnetic waves. So electromagnetic wave, it means that electric field and magnetic field. In terms of electric field, we can write dou square E dou x square is equal to 1 c square. Okay. Dou square E dou t square. Okay. This one is the equation of electric field. E is the electric field. But B is magnetic field. Yeah. So electromagnetic wave is the superposition of electric and magnetic waves. Okay. Dou B square dou x square is equal to 1 c square dou square B dou t square. So B is magnetic field. So this one the example of wave equation. Yeah. So here C or V here is the wave speed. Yeah, the wave speed. So we know that C is wave speed like 3 times 10 power 8 meter per second. Okay. Is equal to speed of light. Okay, the speed of electromagnetic field or speed of light. Okay, and then next is the interference of waves. Yeah. Okay, so this one is interference of waves. Yeah, so interference of wave is the principle of superposition of waves. Yeah. This one is the principle of superposition of waves. So for example, if we have waves one, y1 and x, and then time, yeah. This one is ym sinus kx omega t. Sin kx minus omega t, and then another waves y2. This one is ym sinus kx minus omega t plus pi. Yeah. So we can take the principle of superposition. For example, this one is y prime. Y prime is y1 x point t plus y2 x point t. Okay. So we can add the waves, yeah, y1 and y2. So this one becomes ym sin kx minus omega t plus ym sin kx minus omega t plus pi. Okay. So we remember for the trigonometric function. So for if we have like sin A plus sin B. So this one becomes sinus half A plus B times cos half A minus B, right? Okay. So this one is the trigonometric formula. Right? So here we can write as ym, this one plus this one, it means that sin half, yeah, kx minus omega t plus kx minus omega t plus pi. Yeah. Okay, I think this one is there is two, right? There's two here. Okay. And then times cos half this one, kx minus omega t minus kx minus omega t plus pi. Okay. Yeah, actually this one becomes y prime, yeah, 2ym cos half pi, then sin kx minus omega t plus half of pi. Okay. Yeah, I think this one is the equation of interference. Yeah, can know from this one. Okay. Yeah, this one, right? Okay. So this one called magnitude gives amplitude, and this one is the oscillating term. Expression for interfering waves. Okay. Yeah. So this one, when two waves overlap, we see the resultant wave, not the individual waves. Okay. Okay. And then constructive and destructive interference. So if the phase is the same, it means becomes constructive interference. But if the phase is different, especially different in 180 or p radian, it means destructive waves, like this one. This one is two waves in the same phase, yeah, y1 and y2. So they will make the amplitude higher. Okay. But if they on the different state or different phase, the phase is p radian, it means that they will cancel. Yeah. So this one is the destructive interference, but this one is constructive interference. But another one is intermediate. This one is the intermediate situation with an intermediate result. Okay, if the phase not the same. So it's very important about phase in the waves. Yeah. Okay, and then phasors. Yeah. This one is phase vector. Yeah. Phasor become a rotating vector. Phasor is vector that rotates around its tail, which is pivot at the origin of coordinate system. Yeah. The magnitude of the vector is equal to the amplitude ym of the wave that is represented. Okay. So this one is the snapshot of the two phasors for two waves. Okay, this one's adding the two phasors as vectors gives the resultant phasor of the resultant waves. Okay. So this one is ym1, ym2, and then this one ym prime, and the phase is phi. Okay. Then for the standing waves, so this one is standing waves. You can derive 2ym sin kx cos omega t. One is the oscillating term, and then the 2ym sin kx is the magnitude gives amplitude at position x. Okay. So this one is depends on 2ym sin kx. Okay. But this one is the oscillating term. Yeah. Okay, we can derive the standing waves here. Yeah. So imagine the standing wave y1. This one is at position and time. So this one is ym sin kx minus omega t. Yeah. And then y2 x point t. This one is ym sin kx plus omega t. Okay. So we can add these waves. Okay. Becomes y prime. This one equal to y1 plus y2. X point t plus y2 x point t. Okay. So this one becomes 2ym sin kx cos omega t. Okay. And okay, we call this one is the magnitude of amplitude, and then this one is the oscillating term. Okay. Okay, and then we can determine the nodes and antinodes. Okay, nodes and antinodes for the standing waves. Okay, so imagine nodes and antinodes like this. Okay. Yeah. For example, this one, we can call this one as node. And this one is antinode. Okay, node and antinode. So the position of nodes, we know that nodes is here is half of wavelength. Yeah. Kx is n pi, and then 2 pi per lambda is x. So this one becomes x is n lambda divided to 2. Yeah. Okay. So this one is the position of nodes. Okay. The position of node xn is n lambda divided to 2. So the n is start from 0, 1, 2, and then so on. Okay, this one is the position of nodes. Okay. But for antinodes, can use kx is half of pi. Sometimes 3 divided to pi, 5, and so on. Okay. So kx equal to n plus half pi, or 2p divided to lambda, yeah, times x is equal to n plus half pi. Okay. So we'll get the x is n plus half lambda divided to 2. Okay. Okay, this one is the position of antinodes. So the antinodes, we start from 0, okay? And also start from 0. Okay. Okay. Yeah. Any questions about waves? Okay, and then for the standing waves, we can find the first harmonics and then the second harmonics or third harmonics. Yeah. So for the string here, you can see standing waves. Okay, wave like this we know as first harmonics. Okay. First harmonics. Then another one, in the same length of the waves. Yeah. can see here as the second harmonics. Okay. Yeah, relatively different, but I think it means the same one. Okay. Okay, so this one is the second harmonic, right? And so on. Okay. So this one L is equal to lambda divided 2, but this one is L is equal to lambda. Or you know that 2 times lambda divided 2. So for this first, second, 3, or another, yeah, you can use that the general equation lambda is equal to 2L divided to N. Okay. So this one N is start from 1, 2, 3, or the other. Okay. And then the frequency is V divided to lambda. Okay. So V divided to L times N. This one is the frequency. Yeah. Then remember the velocity. Yeah. You can use the velocity of string. Okay. Velocity of wave at string. Okay. So P here is equal to square root of tau divided to mu. Yeah. Okay, before T is the tension at Newton, and then mu is mass divided to N. Yeah. Okay. Any questions about waves? This one is the then later we will discuss more about sound and the typical waves or mechanical waves, sound. Okay. Okay. I think we can take the exercise. So for example, if we have uh, the equation of transverse wave, like y is 2 at 2 millimeter, yeah, sin 20x minus 600t. Yeah. So the tension of string is 15 Newton. What is the wave speed? Yeah. And then linear density of string. Okay. Yeah. Maybe you can try first. What is the density of string? Okay. So have you finished? Okay, from this one, we can calculate the speed of waves. P is equal to omega divided to K, right? So omega here is 600 divided to 20 becomes 30 meter per second. And then for the linear density, we know that phi is equal to tau divided to mu, right? So this one is 30 equal to 15 divided to mu. Okay. So we can take the square of this one, becomes 900. 15 divided to mu. So mu is 15 divided to 900. Okay. At kilograms per meter. Okay, any questions? Okay. Yeah, I think this one is 1 divided to 60, right? Kilograms per meter. Yeah. Okay. Okay, next is the standing waves, the speed of sound. Okay. So the speed of sound, we know that phi is equal to square root of tau divided to mu. Okay. This one, we know the square root of the elastic property. This one is elastic property divided to inertial property. Okay. So this one is bulk modulus. Okay. So bulk modulus is B minus delta P divided to delta V and V. Yeah. So delta P is the pressure, then delta V divided to V is fractional change. Yeah. Fractional change in volume. Produced by a change in pressure. Yeah. In pressure delta V. Okay. So you know that V is the square root of B divided to rho. Okay. So B is bulk modulus, and then rho is mass density. Okay. Okay, this one is the speed of sound. Okay. Okay. If we know that force. Force is mass times acceleration, right? So this one B is bulk modulus. Yeah. Then we recall again the force is mass times acceleration. So if we have like cylinder, this one is A, and then volume is A times delta X, right? Okay, so it's volume, volume, and then there is a pressure, delta P. Okay, so F is delta P times A. Can use minus delta P times A. A is the area of the site, yeah. And then mass is rho times volume. Okay, delta P divided to delta T. Okay, then you can write minus delta P A times volume. I mean times X. Yeah. Okay, this one is delta X delta V. We can divide this one. Okay. So we get that minus delta P is equal to rho delta X delta T is P delta V. Okay. Then we can calculate the delta V divided to V is A delta V delta T divided to A V delta T. Okay. This one is delta V divided to P. I mean, the difference of velocity is equal to difference of volume. Okay, I mean the capital V is volume, but this one is velocity or speed. Yeah. So delta V becomes delta volume divided to volume times V. Yeah. So this in this equation become minus delta P equal to rho V delta V is this one. Yeah. So minus delta P divided to delta volume per volume is equal to rho V squared. Okay. So this one is the definition of bulk modulus. Okay. So we know that bulk modulus is rho V squared. Okay. This one is B rho V squared. This one is bulk modulus. Okay, and then next is the speed of sound depends to the temperature. Okay, so we can use the speed of sound depends on the temperature. Okay. Speed of sound on depends to the temperature. Okay. Okay, it means that we can calculate the phi here is around 331 meter per second. This one is the standard velocity of sound. Yeah. Square root of 1 plus Tc divided to 273 degrees Celsius. Okay. So Tc is temperature in degrees Celsius. Yeah. So 331 meter per second is the speed of sound. Yeah. At 0 degrees Celsius. It means that higher temperature will be uh, higher speed. Yeah. Okay. So for example, if we have TC, TC for example 20 degrees Celsius, we can calculate the velocity of sound around 343 meter per second. Yeah. 343 meter per second. Okay. Then next is the speed of sound in solid. Okay. Okay. Speed of sound in solids. So for example, is aluminum bar. Okay. So what is example of aluminum bar? So we can calculate the speed is equal to square root of y divided to rho. Okay. So y here is Young modulus. Okay. And then rho is the mass density. Yeah. So you can calculate the speed of sound at solid materials by using V is equal to y divided to rho. Okay, so for example, for aluminum bar, we know that the Young modulus is around 7 times 10 power 9 Newton per meter square. And then rho of aluminum is 2.7 times 10 power 3 kilograms meter cubic. Okay. So we can calculate the velocity of sound or speed of sound at aluminum. V is square root of y divided to rho. Okay. So this one is 7 times 10 or 10 divided to 2.7. 3 power 3, 10 power 3. So this one is around 1.4 kilometer per second. Okay. So this one is the speed of sound at aluminum. Okay. And then the example of speed of sound in liquid. Yeah. Speed of sound in liquid. Okay, for example, if we want to measure the speed of sound at water. Yeah. Speed of sound at water, we know that the bulk modulus of water is 2.1 times 10 power 9 Newton per meter square. And then rho of water is 10 power 3 kilograms per meter cubic. Yeah. So this one is water. Then you can calculate the speed of sound at water. Square root of B per rho. And this one is 2.1 times 10 power 9. 10 power 3. Okay. So this one similar. Yeah, I think this one is around 1.4 also at kilometer per second. Okay, this one is speed of sound. Yeah, like this, right? Sound waves. This one is the kind of longitudinal wave, mechanical waves that can travel through solid, liquids, or gas. So no S is the point of source. Yeah, that emit sound waves at all direction. Sound wave travels from a point source S through a three-dimensional medium. This one is called wavefronts. Okay. So wavefront is the direction of the ray. Okay. And then we have already verified the bulk modulus and rho and the speed of sound at liquid. Okay. So this one traveling sound waves. Okay. Sound wave displacement expression. Yeah, this one is similar to wave general wave equation. Sm cos kx minus omega t. Okay, but in this case, this one is sound. Yeah, this one is the amplitude, right? Then pressure delta Pm sin kx minus omega t, where the pressure amplitude is this one. Okay. And then interference, constructive and destructive, and then intensity and sound level. Yeah. So intensity is power divided to area, right? Divided to area. Okay. So we get that intensity is half rho v omega square S max square. Okay. Then this one is the intensity. Intensity is power divided to 4 pi r square. Yeah. 4 pi r square is the area of sphere. Okay. Like ball. Okay. This one is the area of surface of the ball. Okay. And then hearing limits or decibel scale. Yeah. This one is sound level. The sound level is 10 decibel log I divided to I0. Okay. So the I0 is reference intensity level. Then this one is the hearing threshold. Okay. Yeah. And then beats. Yes. Okay, beat is the difference of frequency. Yeah. For example, F1 minus F2. So it's a bit frequency, and then Doppler effect. Okay. So Doppler effect we can calculate like this. Okay. This one is the moving source stationary and source moving detector stationary. Okay. Yeah. Okay, so for the periodic sound waves, yeah, can use the equation. This one is periodic sound waves. Okay. So periodic sound waves. This one is the harmonic displacement function. Yeah. Can see that S x point t is equal to S max cos kx minus omega t. Okay. And then the pressure delta P max sin kx minus omega t, right? And then delta P max. So the relation is rho v omega S max. Yeah. And then delta P is equal to bulk modulus delta V delta VI. Okay. So delta P, yeah, is equal to minus B delta V VI minus B delta V is A delta S, yeah, divided to A delta x. This one becomes minus b delta s delta x. Okay, so we'll get that the pressure delta P is equal to minus B uh, delta S delta X, or we can call dulu X. Yeah. S is S max cos kx minus omega t. Okay. So we can take the derivative of this one. Okay. Becomes delta P. Cos becomes minus sin. Minus and minus becomes positive. Okay. So BK S max sin kx minus omega t. Okay. Okay. By this one, yeah, we can use the delta P. BKX max sin of kx minus omega t. So this one is rho p square. Yeah. K. So B is rho p square, right? And then S max sin kx minus omega t. Yeah. So this one rho p square K is omega divided to P S max sin kx minus omega t. Yeah. This one become we can divide this one. Rho p omega S max sin kx minus omega t. Okay. So one is delta p. Yeah. So delta p is delta p max sin kx minus omega t. Okay. So this one is delta p max. Yeah. Okay. So we get this equation. Yeah. Yeah. This equation then. Oh, sorry. I mean this one. Yeah. We get this equation from this one. Yeah. Okay. So the Doppler effect, I think this one is also important. Yeah. Uh, so the Doppler effect, we identify the shift of detected frequency. Yeah. Identify the calculating of Doppler shift and calculate the shift of sound frequency. So for the Doppler effect, okay, so for example, if we have the source of sound, yeah, okay, this one is velocity of the source. And then another one is people. Yeah. For example, in this one, people. So here is the velocity of observer. Yeah. Okay. So the frequency will be different. Here the frequency f prime is equal to v prime divided to lambda. So this one is the v of sound, yeah, here. The velocity of the speed of sound, and then VO we call the velocity of observer. Yeah. Velocity of the observer. So this one becomes V plus VO divided to lambda. Yeah. So the velocity will be higher if the direction is cosine. Yeah. But for the regular frequency, it's V divided to lambda, right? So we can take that lambda as V divided to original frequency. So it becomes V prime V plus VO divided to lambda. Lambda is V times frequency. Yeah. Okay, or we can write V prime is 1 plus VO divided to V times frequency. Okay. So this one, the kind of observer moving towards source. Right? Yeah. So this one is the observer is toward the source, but how if the observer moving away from the source? So if the observer moving away from the source, we can use that V prime is equal to V minus V0 or V. So it becomes the frequency is 1 minus VO E times F. And this one is for observer moving away from the source. Okay, this one is observer moving away from the source. Okay, but how about the wavelength? Yeah, lambda. Yeah. Can calculate the wavelength. Uh, so in this case, the source in motion, yeah, but the observer at the rest. Yeah. At rest. At rest. I mean, it's not in motion. Yeah. So we know that lambda prime is equal to lambda minus delta lambda. Lambda minus V sound divided to frequency. And we can calculate the F prime frequency. Yeah. V divided to P minus V source. Okay. Times frequency. So this one becomes P divided to V, P divided to V minus Vs divided to V times frequency. Okay. So F prime becomes 1 divided to 1 minus V source divided to V times frequency. Yeah. Then F prime becomes 1 divided to 1 plus V source divided to V times frequency. Okay, this one for the source moving toward the observer, but this one source moving away from the observer. So this one for source moving to the observer, but this one source moving away from the observer. Okay, then we can take the general formula from here. Yeah. So for general formula for flow effect, can write as F prime is equal to P plus or minus P observer, P plus minus P source times the frequency, original frequency of the source. Yeah. Okay, this one is if the observer and the source in moving here is not in rise. Okay. So in this case, frequency, yeah, by the observer. Yeah. Observer and source in motion. Okay. This one is the Doppler effect. Okay. Okay. Any questions about Doppler effect? Okay, so we can see the shift of source, yeah, of frequency lambda and supersonic speeds and shock waves. Yeah, I think we can take the conclusion, yeah, for the waves and mechanical waves. Okay, so waves we can divide to transverse wave and longitudinal waves. Then wave speed. Yeah. We have studied about the equation of waves, then wave power, and another formulation. Okay. questions for our lecture today? And the contact group, then you can check the mask and which line of the participation. Okay, I think that's all for in today. Yeah. Thank you for attention. See you again next week. Yeah. Okay.